that we have one of their instruments in the MIC. And so we'll have Robert Stroud from NanoMegas give the next presentation. Robert, are you available?
Yes, I don't know if you noticed, I had a computer problem, right? Like a minute before I was supposed to start. So that was exciting.
Okay. No problem. Are you all set to go, or do you need some time?
I think so. It'll be interesting to see if my presentation comes up, but I am ready to start. Absolutely.
Okay, well then go ahead. Thanks again for coming.
Okay, great. I'm assuming you can see my title slide.
Yes, it looks great.
All right, awesome. First of all, I'd like to thank everyone for the opportunity to talk about the NanoMegas precession electron diffraction system and the technique, talk a little bit about how it's used for some other applications, help you understand what we're doing with it. I did want to start out by telling you I would have much rather been in Texas giving this talk. It was 35 degrees this morning here in Boise, so could use a little more warmth. All right. So there's a lot of different applications. We go into different spaces. I have a few slides here that just kind of give a nice overview if you're new to the system or you're new to what the precession technique does. This is an example of some semiconductor devices showing orientation. We also have people working in geology. This is a phosphorite, and there's some mapping of the phase and the orientation in that mineral. There's also nuclear energy applications. This is showing some martensitic layer and some austenitic weld material and what the different makeups of those are. There's also biological application. This happens to be a bone. And so there is work with beam sensitive materials. With NanoMegas, we offer a system for TEM that uses precession electron diffraction, and it enables a lot of different applications. And in general, there's two types of things that you can think about, and that's what I'd call cross-correlation techniques and structural determination techniques. So the A-star system allows you to do orientation and phase mapping, much like EBSD does in SEM. You can also do strain analysis. And then the company started as a hardware software provider for crystallography. It was started by crystallographers. And so there's still applications where you can do 3D tomography with diffraction data. You can do pairs distribution. So we still work in not only these mapping applications, but in structural determination. All right, just so we're all on the same page, I'm assuming most people know this, but maybe it's a good review. You have a sample in the TEM, the image is put down here on the image plane, but we work in the diffraction plane. So that's reciprocal space, and we essentially put a TEM into that mode, diffraction mode, and we do everything from there, looking at the sample using reflections. One of the issues with TEM is that if you do a structure factor calculation, you'll have forbidden reflections. That's shown by these little circles. And those are kinematically, they shouldn't exist due to cancellations in the diffraction interference. But here you see more reality, you get reflections. So you have dynamic component that makes it difficult to work with a TEM pattern, diffraction pattern. Here's another example of silicon. You do your structure factor calculation. For some reason, that forbidden reflection shows up. So what can we do? We have a hardware software solution that takes a standard TEM diffraction pattern, and by putting signals on the beam coils above the sample, we can precess or rotate the beam at a small angle off axis, and we get disks. And then you do counter precession using the image deflectors to stabilize so that you end up with a quasi-kinematical diffraction pattern. And then that opens up a lot of the applications I'll talk about for using template matching. This is an example of what precession does. This is a, I guess I have to turn off the pointer here. Let's go back. So this is I think it's mayanite. It's a mineral, and cubic, I believe. And it, as you see, the precession signal is increased from 0 degrees to something like 3 degrees. You illuminate more reciprocal space, and then towards the end, even the human eye can start to pick out intensity differences. And this just kind of help you figure out what precession does. This is the scanning coils, the descanning coils. We rock the beam off axis, and you can see that Ewald sphere is now illuminating a portion of the lattice that only has, or has a reduced dynamical component, more kinematical. And then we spin that at high frequency, 100 Hertz. And when you do that, you develop what I mentioned were quasi-kinematical diffraction patterns. And just a schematic to kind of remind you, on the microscope, we have a camera, it looks at these diffraction patterns, we talk to coils, and we're interacting with your specimen here. So what does the user do? The user has an interface, which is a virtual stim image. So this is created by taking a center spot from a diffraction pattern at every pixel point and recreating a map of your sample. So you would use this to position an area of interest, to figure out where you're looking on your sample. One of the really nice features about this, and it opens up a lot of interactive work with your sample, is you can put your cursor on any location, and then obviously this isn't live, but if it was a live image connected to a microscope, you'd see a change in diffraction patterns. And that's very good, because then you can look, is this the grain I'm interested in? Is it on this zone? Is it off zone? Is that a different material? Are the reflections good? So you can do a lot of things just by kind of poking around here to see what's happening in your sample. And then if you're going to do an orientation map, you're going to need some templates to match to. So you'll input some parameters. You need unit cell information, space group. You need to know what atoms are there, what the occupancy is, and then the software generates a series of possible templates from all of orientations. And then those are matched against acquired data, and the best fit will give you a solution. And then depending on symmetry, if you have triclinic or monoclinic, something, you're going to use much more of reciprocal space, but for cubic things with high symmetry, you need a very small amount of reciprocal space to define the possible orientations. What's interesting about TEM is, unlike SEM approaches, is that because you go through the sample, you're getting data through the entire volume. And so, for example, if you come across a grain, you're going to see where the orientation will suddenly change to a different orientation. So this, in this case, is showing a 60-degree shift, but the reliability goes to 0 because there's 2 equally valid solutions. So you can use that to your advantage, because you can see not only one possible solution, which could be one grain, you could see another one, which is another grain. And so we have some capability of dealing with overlaps, looking at grain boundaries, and finding what's the best solution for that particular location. This is a nice example. It's not particularly high resolution, but I think it's a very a good way of showing what you can do. This is a photovoltaic device, and on the left you can see the orientation map and the different directions that are highlighted corresponding to different colors. And then you also have a phase map, and this is showing the cadmium telluride, tin oxide, and then some other possible phases that were tried to map into this area here. This is a what I would call a high resolution image compared to the last one. It's a hafnium niobium multi-layer. You can see the little 3 nanometer hafnium here, and also the orientation for both of those phases. This is some work that was done at UC Santa Barbara, and this is a copper niobium system. What you can see is here is a virtual bright field. So it's an image created from the diffraction patterns. And then you have the different layers of this immiscible copper niobium material, and then what the orientation of all those different grains are. This is gotta go forward again. Here we are. So this is I think a highest resolution orientation image I'm aware of. It shows some copper material. This is a semiconductor back end and a 2 nanometer twin. You can see that as you step across with that line scan A to B, that there's a 60-degree orientation change as you go across the twin, and you can see the length scale here that we're working with. You can also do things like cross correlation, where you compare diffraction information with all the adjacent pixels. You get a projection of what's going on inside the area of interest. So these are gold nanoparticles, and you can actually see what's happening at the interface of each of those. I have a short story, application story, that I think is interesting. It kind of illustrates the power of the precession system. This is a lithiation in an iron phosphate. And so this is a battery problem. We're trying to understand how the intercalation works with the lithium. This is an older study, maybe 10 years ago, but it was, there was a lot of debate of how the lithium goes in and out of these batteries, what was the mechanism. And so you need to be able to map the two phases. The problem in diffraction space is that the unit cells are almost the same, maybe 5% difference. And so without precession, you're not able to pick up little differences in these high order reflections out here. So you can see this was required, the precession system. You need these higher order reflections, more kinematically correct patterns to map those two phases. And then the culmination of all that work is they were able to show how the lithium went in and out of these particles, and it supported this so-called domino cascade model. And then I just have a couple examples of some other applications. This is polysilicon grain boundaries. So in addition to orientation, you can automatically generate grain statistics. So you can get a distribution of what the grains are. You can map twins and do other work with your sample. And then I thought this might be interesting. This is a protochips liquid holder. This is some work we did in Europe last year, and we actually were able to map orientation of nanoparticles in a liquid and get very nice results. So it was a surprise to everyone that you could maintain the positioning of these particles in the liquid long enough to do the maps. And then I'll talk very quickly about some of the other things we're doing. So we have strain application. Strain, it works very similar to the orientation in that you're matching an acquired diffraction pattern to another data set. So in the case of orientation, it's a generated template. In strain, it's a unstrained area of your sample. And so the reason that the precession is used is because this is a silicon germanium wafer, and in this, or silicon bulk, silicon germanium blanket wafer. In this area, the same material, silicon germanium, but the precession off case, you can see the reflections are sometimes very different. If you're trying to calculate strain by looking at a distance to a reflection, in one case, it might not even exist in the other. But with precession, you get rid of those bending effects, thickness effects, and you get a consistent diffraction pattern in similar locations. And so what do? We take a reference area, like in the previous slide, it would have been a bulk silicon, and you compare that to a strained area, and then you get a distortion matrix, which allows you to figure out what the strain was in the sample. This is an NMOS sample from Texas Instruments and we did some initial work with them, and you can see up in this gate area, there's a line scan through here. So this is the actual strain map, and you can see very nice resolution and plot of what the strain is in XX and YY directions. And then you have a goodness of fit here. I believe that Dr. Shi will talk about some other applications in non-semiconductor devices of strain, because that's also possible. And then I'll just briefly mention some of the other things we do at NanoMegas. We have a diffraction solution for doing tomography to solve structures. So it's analogous to image tomography, but you put together HKLs and intensities and create a 3D volume. And if you have plus or minus 50 to 70 degrees of tilt, you can solve space group, but with as little as plus or minus 15 degrees of tilt, you can solve point group. And then this is just a nice visual to show you what's possible. We're all used to looking at diffraction patterns in this way, but with this superconductive material, you'll see that you actually have a 3D volume of reciprocal information, allows you to solve structures ab initio. So this is single particle work, where before you're mapping multiple particles. This is just trying to solve a particular material. And then lastly, I'll mention we have solutions for electron pairs distribution function. So with electron pairs distribution function, in many ways, when you're working with short range order, amorphous material, you get a diffraction pattern that looks a lot like an X-ray. So you can see a lot of similarities between two theta plots in XRD, but now you're working with electron pairs distribution function, and you're able to work out nearest neighbors and bond lengths from that. And we'll also be offering some mapping software for this in probably the end of the year, early next year. So that's a very quick overview of what the technique is, how it works, how it connects to a microscope, some of the other things NanoMegas is doing. And I'd take any questions that anybody had. I know that Professor Shi is going to give a lot of detail with some of his specific applications, and I'm looking forward to that in the next talk.
Thank you so much, Robert. We do have time for questions if anybody has any questions.
Oh, that's fine. I'm sure that people, if they do, they know how to get a hold of Professor Shi, and they can get a hold of me, and we can happily help at some other time.
That's great. And just a reminder to everyone that Dr. Shi will be doing a demonstration of the A-star this afternoon at 2 o'clock. And so it'll be on this same Zoom link. And so in addition to his talk, which will be following this one, we'll also get that demonstration to show things in action. Okay, thank you so much, Robert. And we really appreciate you being able to participate with us. And that was really a great talk, so thank you. And it's a great introduction for our next speaker.